Hi everybody, Physics Ninja here. Are you currently studying for a kinematics test? Well, you came to the right video. So this is going to be a practice exam test. What I want you to do is go in the comments section down below. I have a link to a 1D kinematics exam. Start by working out the solutions yourself and then come back and watch my solutions. Okay, compare them, see if we got the same thing. All right, like with all my videos, give it a thumbs up if you like it. Consider subscribing to my channel. Okay, let's get started. All right, problem one, a car accelerates from rest up to a speed of 15 meters per second in 2.5 seconds. What is the acceleration? All right, so that's kind of a key word, right? You start from rest. We're going to start with the definition of acceleration, right? This is a calculation. You can see all the answers are numbers. It's the change of velocity over the change in time, right? Our change of velocity here, our final was 15, and a change is always a final over minus an initial over the change in time. Okay, so we've got 15. We started from rest, so we were at 0 and over 2.5 seconds. All right, you put that one in the calculator, you should get 6 meters per second squared. Okay, so correct answer for this one here should be D is the correct answer. All right, let's look at problem 2. Problem 2 says the motion of a particle below is shown. All right, the particle's acceleration is... All right, so it's kind of a similar problem. We're asking for the acceleration. We could apply the same kind of formula, and we're given a graph over here of velocity versus time. Okay, so if you're given a velocity versus time graph, the question is, how do you calculate the acceleration? Remember, this one here you should know. You should know that this is the slope of velocity versus time. Okay, and this is also what it looks like, right? Delta V over delta T would be a slope. So first thing here, we notice that the slope is a negative, okay? And the slope is the same everywhere, right? If I take the slope kind of over here or over here, it doesn't matter. It's the same everywhere. So is the slope positive and constant? Nope, okay? Is the slope positive and increasing? Nope. So is the slope negative and decreasing? Okay, the function is decreasing, but the slope is always the same, okay? So actually, if you look at the next one, it's negative and it's constant, right? The slope is constant. So that's kind of the correct one. Forget about 0. All right, let's keep moving. All right, question 3 to 7 refer to these 4 graphs over here. So let's kind of work on those. All right, so we've got kind of 4 velocity versus time graphs. So let's keep that in mind. All right, which object is slowing down? So if you're slowing down, your speed should be getting smaller, right? So which one has a speed that is getting smaller? It's got to be this one, right? You started off here at 30, and then you ended off here at 20 after 3 seconds. All of these other ones here, B and C, are increasing, and the first one is constant. All right, so D is the correct answer for the third one. Okay, so which object has the greatest absolute value of acceleration? All right, so now we're going to go back to our definition of acceleration. Remember, it is the slope of a velocity versus time graph. And if you look at it here, this is probably the one with the greatest slope, even without doing the calculation, just by looking at the graph. All right, so I think C is the correct answer for this one. So for 4, we should go ahead and do C, has the biggest slope. All right, compared to the average velocity of C, the average velocity of B is what? Is it the same, less, greater? Okay, so we're comparing both of these, and we want to know the average velocity. Do you know how to calculate the average velocity if it's changing? So if I think about an equation for the average velocity, now if it's changing at a constant rate like this, so the acceleration is constant, it's just 1/2 v initial plus v final, all right? You just kind of add them up and then divide by 2, okay? This is 0 and this one is 30. If I divide that by 2, it's like the average is right here, 15. This one here starts at 10. This one here goes to 30. So the average here would be 20. Okay, so clearly B is bigger. Okay, so the average velocity of, the average velocity of B should be greater. Okay, so C should be the correct answer for number 5. All right, let's keep going. Number 6. Which object traveled the greatest distance in the 3-second time interval? So the 3 seconds is basically the whole graph, right? Now, if we're looking for which one travels the greatest distance, for that, you should be thinking about the displacement. And how do you calculate the displacement if you have a velocity versus time graph? You have to remember that it is the area under the curve. Okay. All right, so which one has the greatest area under the curve? Well, just looking at them over here, I mean, these ones, without even doing the calculation, certainly not C, right? And if you look at the last one over here, the last one, look at this, has a lot of area under the curve, right? Just by inspection here, I think you should be able to answer this one, right? Without doing the calculation. It has to have more than A, right? So for number 6, I think D is the correct answer for that one. So let's go ahead and circle that answer. All right, and our last one for this section, which object was neither accelerating nor decelerating? So what they mean here is that the acceleration of that particle or that object should be 0. That means, again, that the slope should also be equal to 0, and there's only one, right? This is the one where the slope is 0. So for 7, you have to go with A. All right, good work. Let's keep going. All right, question 8 says a runner jogs east at 8 meters per second for 60 seconds, and then west 5 meters per second for 30 seconds. What is the average speed? All right, so the key word here is average speed. How do you calculate average speed? All right, so this is a definition, okay? So the average speed, how would I write this? Average kind of speed here. The definition is total distance traveled, all right? Total distance, let me just write it all out, over the total time, okay? Over the time that it takes. So what is the total distance traveled? So first of all, you're going this way, you're going east at 8 meters per second for 60 seconds. Right? And then you turn around and you go the other way, right? You're going west now. You're going this way at 5 meters per second multiplied by 30 seconds, all right, to get the distance. All right, so at the end, just substitute over here. We'll keep working at it. So the distance here traveled for the east travel is the speed multiplied by the time, right? That gives you a distance. Plus the total distance traveled over here when I'm going west is going to be 5 multiplied by 30. And then at the end, I got to divide by the total time for that trip. The total time is 60 plus 30. Gives me 90 seconds for the whole trip. I put all that in the calculator. I think you should get 7.0 meters per second. Is that one of the choices? And it is, okay? So choice B is the correct answer for this one. All right, good. All right, let's keep moving. Number 9. Let's scroll down here a little bit. All right, for question 9, what we have here is a cruise ship decelerates, all right, at this rate of 0.2 meters per second squared for 30 seconds. The ship's speed after that deceleration is 12 meters per second. What is the speed just before the deceleration? Well, okay, so this sounds like we can use one of our kinematic equations, right? Plus acceleration times t. All right, so we know after the deceleration, this here has to really be the final speed. They want to know the speed just before. What we're looking for here is really this initial acceleration. Let me go ahead and substitute our numbers. First things first, this here is 12 v initial. And the deceleration here, or the acceleration, is minus 0.2 multiplied by the time. Actually, let's just go ahead and substitute the time in right away, which is 30 seconds. All right, you got to bring this term on the other side. We're going to get V initial is 12 plus 0.2 multiplied by 30. 0.2 multiplied by 30 is 6, so this should be 18 meters per second is my initial velocity. Okay, correct answer for number 9 should be choice E. All right, let's read the next one. Which of the following statements concerning a body's velocity and acceleration is not possible? Can you have an instantaneous velocity to the east and a westernly? Absolutely, right? This would just mean you're slowing down. Can you have an instantaneous velocity to the west? Sure, this would mean you're just slowing down when you're moving in the opposite direction. Can you have a changing velocity and a changing acceleration? There's nothing that stops you from doing that. A changing velocity and a constant acceleration. Can you have that? right? A changing velocity and a constant, yeah, that happens all the time. For example, in free fall, right? The acceleration is constant and the velocity changes. Check out the last one, a constant velocity and a changing acceleration. So if you have a constant velocity, remember what that means. That by definition, you are saying that the acceleration is zero if the velocity is constant. Okay, so this one here does not make sense. Okay, so this is really, really not possible. Okay, so E is the correct answer for that one. All right, let's keep going with number 11. We have a calculation here. We have an object is shot vertically upward in the air with a positive initial velocity. So it kind of looks like this. Which of the following correctly describes the sign of the velocity and the acceleration at the maximum height? All right, so here's the object going up. Let's just kind of draw a quick cartoon, and we're looking at it right here. That's at the top, right? The maximum height, by the definition, is the top of the trajectory. So what would we have at the top? You should know something about the top, that v has to be equal to 0. And what else do you know about the acceleration everywhere? The acceleration is little g, right? And little g is always down, even at the top, okay? So really, I think the best choice here has to be 0 velocity at the top, right? That's at the highest point. And the acceleration is negative a. That just means that it's going down, okay? That it's slowing down, and it's constant everywhere. It's always the same, down. B is the correct answer for that one. All right, let's keep going. Let's finish these off here. All right, for number 12, we have here, it says a ball is dropped off a cliff. After t seconds, it's achieved a final velocity v and a displacement d. If the time of the experiment were doubled, what would be the ball's displacement? So this is what we have. We have two scenarios. All right, 1 and 2. Let's write down what we know for each one. The equation that I'm going to use here is going to be d is 1/2. The acceleration is little g, and t squared. There's no initial velocity term because I've dropped the ball, right? So that initial velocity is 0. What else do we know? The velocity is v at the end, and the displacement is d. Okay. Now what happens if you double the time, for example? Right? In this case over here, if I double the time, let me just switch the color here. In this case, if I double the time, the acceleration is the same, but what happens? Right? I double the time, so that becomes 2t. Well, when you square that value, guess what you're going to have? Right? You're going to get a factor of 4, and here you're going to have t squared. Let's take this 4 and stick it out in the front, and I'll group all the other terms together because I want to compare it to the previous displacement. Right? So you can see that the displacement over here is going to be 4 times, because this guy here is nothing more than the green displacement for case number 1. All right, so you're really going to get 4 times that distance. Okay, so D here is the correct answer. You're going to have 4 times the displacement for this problem. So D is the correct answer. 13, a ball is dropped off a cliff again. Okay, that's one of our key words. Initial velocity is 0. After t seconds, it's achieved the final velocity of v and a displacement d. If the time of the experiment were doubled to 2t, okay, now they're asking for the final velocity. Again, we're going to use another kinematic equation, okay? One of them looks like this, except we have a simplification for this problem that initial velocity is 0. Little g is constant, right? It's 9.8. So what happens now if I double the time? Well, my final velocity will be, right, minus little g multiplied by the time, which is now doubled, 2t. Again, if you stick that factor 2 out in the front, what you're going to get here is negative g times t. And this here is nothing more than the velocity in the first case. Okay, so you should double the velocity in this case. So B, I think, is the best answer for number 13. All right, we got 2 more. Let's keep going. All right. In the absence of air resistance, an object dropped near the surface of the Earth experiences a constant downward acceleration. All right, so they want to know what that actually means. Does it mean that the speed of the object increases 9.8 during each second? Right, remember our definition of acceleration, right? It tells you how the velocity changes for every single time. So actually, this one looks good to me. Let's read the other ones. Does it mean that the speed of the object as it falls is 9.8? Well, no, this would be a constant speed, and the speed is not constant. Object falls 9.8 meters during each second. Well, it really has nothing to do with that. That might be true for the first second, but it's not true for every other second, right? Because it speeds up as it keeps dropping. Object falls, no, forget about all this stuff. Object falls during the first second only. Well, again, imagine you were going to just calculate it, right? Little gt squared. The amount that you drop in the first second is actually little g over 2, right? Because you substitute 1 over here. So you're actually going 4.9 meters in the first second. So it's really A, I think, is the best choice for number 14. All right, let's keep going. And our last multiple choice problem over here says a particle decelerates from an initial speed of 5 meters per second to a stop, and it covers 25 meters. What is its acceleration? All right, so again, I'm going to use one of the kinematic equations. The one I'll use in this case is v final squared. Is v initial squared plus 2 times the acceleration multiplied by my displacement. Let's look at what we know and what we don't know. We're just trying to find the acceleration over here. So we can substitute our numbers. The initial speed was 5 squared. Our final is 0, okay? And plus 2 times 25 is the displacement, and I'm still left with the acceleration down over here. So bring that on the other side. You can, right away, you're going to see you're going to get 25 for that 5 squared. And then you have to divide through by this term here. That's 2 times 25, which is 50. Okay, so you should get, oh, and look at, the important thing here is this is also a negative, right? When I bring this guy on the other side of the equation, I have to get a negative, and all the answers are negative there. So you should get 0.5, right? Negative 0.5 meters per second squared. Okay, so the correct answer for this one should be D. All right, great. All right, let's look at the problems now. All right, a ball is thrown atop a 400-meter building upward at an initial velocity of 25 meters per second. The first thing says complete a position versus time graph and a velocity versus time graph for this particular motion. So I've got it sketched out here. In order to kind of plot these things, it's kind of useful to know a few things, right? What is the maximum height, right? So let's go ahead and start that. I start on a building that's 400, but how do I calculate the maximum height? So for this one here, there's many ways of doing this. I'm going to choose what is the displacement, okay? How do I calculate that displacement? Well, I can use one of my kinematic equations, right? It's the initial velocity multiplied by time minus 1/2 gt squared. And what I need to do, so I know this is 25, this is 9.8, but I need to know which time do I substitute in there. And one thing you should know is that the time to the top, well, remember, time to the top is determined by using this, by noting that the final velocity at the top is 0. All right, and if I think about the velocity expression as a function of time, this is what it looks like. Okay, so this is always the same. So you set this side to 0, and then you solve for the time. Okay, so the time to go to the top is that initial velocity divided by little g, which in this case is nothing more than positive 25 for that initial velocity, and divided by 9.8. This gives me a time of 2.55 seconds. So at 2.55 seconds, this is where I am at the top. I can now calculate what this displacement is. So the displacement that I'm calculating using that equation is this one, okay? Because I start over here, and this is really the delta y that I'm calculating if I substitute the time equals to 2.55 seconds. So if I go ahead and do that, this is what it looks like. So 25 for that initial speed, 2.55, and minus 1/2, 9.8. And again, 2.55, don't forget to square it on this last term. All right, if I did that calculation correctly, I should have 31.9 meters as my displacement. Again, that's from the top of the building, right? It's not from the ground. I started 400 meters above the ground. All right, so we're doing pretty good. And maybe the last thing I may want to calculate just to complete these figures over here is how fast am I moving just before I hit the ground, right? What is the V final here in this figure? Okay, so in order to calculate this, well, what you want to do now is you need to calculate Remember at the top here, we know the speed is 0, right? V top is equal to 0. And what if I calculate how much time does it take to go from the top all the way to the bottom? I know that this whole distance over here, right, the whole distance that I'm going to drop is going to be 431.9 meters, right? That's the whole drop. So I could probably calculate how much time does it take to drop this amount. And in order to do that, I'm going to use my delta y equation because I know the displacement now, minus 1/2 little gt squared. Now this will be minus 431.9 because it's going down, okay? And I want to solve this for the time. So the time should look something like this. If I just do a little bit of the algebra here, we have 2 times the displacement over little g. Okay. There's still a negative over there. And you see that the negatives are going to end up canceling out here because I have minus 2. My displacement is minus 431.9 and over 9.8. After I do that math, I should get a time of approximately 9.39 seconds. Okay, so I'm now in a position to calculate what is the speed here down at the bottom. Okay, let's give myself a little bit more space. So the final velocity just before hitting the ground here, again, I have an initial velocity. Again, this is measured from the top, right? Let me just make a note here. From the top, minus little g times t. So if I measure from the top, forget about that guy. Minus 9.8 multiplied by 9.39 seconds. My final velocity when I hit the ground is going to be approximately minus 92 meters per second. Negative is indicating that it is going down. Okay. Another way I could have done that one is using one of the kinematic equations. Kind of an alternate solution here. You might have chosen just to use this one, v final squared equals v initial squared, minus 2 times the displacement times little g. Okay. If I was going to do that one, my final velocity. All right, so what would I choose? I could choose the initial point now. The initial point here was a 25 meters per second velocity going up. Minus 2 times, and the displacement here, if I'm just starting from this initial point over here, my displacement for this one here would be minus 400 and multiplied by 9.8. All right, you put that in the calculator and you're going to get the exact same number. You're going to get 92, but remember when you take a square root, you have to go plus or minus. All right, there's always 2 solutions to a square root, and in this case here, I'd really have to take the negative sign. Okay, the correct answer would be minus 92 meters per second because I am going down at the end. All right, so now we have to sketch the graphs, okay? In order to sketch the graphs, so we have position versus time. Let's do that at time 0. Let's assume here that I'm starting over here at 400. I'm just going to do a quick sketch. I know that I'm going to go up to a maximum, okay? I'm going to go up to the maximum, and this guy right here should be a 431.9. At this specific time here, we've calculated how much time it takes. This is 2.55, okay? I also calculate the time that it's going to hit the ground, okay? It's going to hit the ground, well, now you have to be a little bit careful, right? The time it takes to hit the ground is not 9.39. 9.39 is actually this guy right here, right? This here is the 9.39 seconds because it's the time from the drop all the way to the bottom. Okay, so in order to get the total time over here, you simply have to add both of those numbers. All right, so that gives me 11.94 if I add both of those numbers, the 939 and the 2.55 seconds. All right, time to the top, time to go from the top to the bottom. That's the total time. All right, let's go ahead and just kind of do a sketch here. I'll try to do that. It should be an inverted parabola, right? Something like this. All right, it's pretty easy. All right, how about the velocity? Well, the velocity, again, I'm going to start over here. I'm going to start here. We had an initial velocity of positive 25. All right, we know that once I get to the top at this 2.55, I'll do that at the same scale. It's at the third one. At the third one, I should have 0 meters per second because I'm at the top. Okay, so it should be a graph that goes through there. And right at the end, oh, well, this is going to be a little bit hard. I'll just plot it like this. Let's keep that line going. First of all, this should be a straight line. So I didn't kind of choose the right scale over here. I may get docked a point. But right over here, I should be going at, once the time is 11.94 seconds from the top, okay? From the point where I launched the object, I should be going at minus 92 meters per second. All right, so let's go ahead and draw that line. I'll make this one in blue, so I should have a straight line, right? Should have a straight line. Guess what? The slope is nothing more than the acceleration. That should be little g, which is minus 9.8 meters per second squared. You can go ahead and draw the axes here. Imagine here I have time over here, and I have velocity like this. Okay, I think this would kind of be a good sketch. Maybe go ahead and mark the time here when I'm 2.55. Again, I'm just doing a quick sketch here. You could probably do a better job than that. All right, let's go on to the next one. How far above the ground, let me scroll down, is the ball at 6 seconds? All right, so guess what? All we have to do now is just use one of our kinematic equations. What we're given here is the time, okay? So right away, you should be thinking about the kinematic equation that you're going to use. For this one, I'm going to use delta y is equal to initial velocity multiplied by time. What else? Minus 1/2 little g multiplied by t squared. Again, this is a displacement that I'm calculating, right? It's not necessarily the position because I'm starting at 400 meters high, but let's substitute our numbers and see what we get. All right, we're going to get 25 is that initial velocity. Now we substitute 6. This is 9.8. And then I go with 6 squared. If I substitute everything in here correctly, I should get minus 26.4 meters. All right, let's go ahead and highlight that term. Why is it negative? Negative simply tells me that relative to where I start, I have moved down 26.4 meters. Well, remember, you started at a high cliff, right? This is what it looked like when I started. I was at the top of 400-meter cliff. And now what I've done is I've moved down 26.4 meters. So the question is, how high are you from the ground, for example? What is this height? Well, you know that if I add whatever number here to 26.4, I have to have 400. All right, so if you do that math, you should get 373.6 meters. This is really my position here above the ground because they explicitly asked that in the problem. All right, so this would be 373.6 meters. So be a little bit careful, right? When you're calculating delta y, it really is a displacement relative to where you started. All right, and problem D says another ball is thrown downward at the same height at 25 meters per second at the same time as the ball is thrown upward. So now we're going to go down, right? All right, so what are we going to do in this case? So let's compare some of these choices. Which ball hits the ground first, right? So we have kind of ball number 1, which went up, and now we're going to have ball number 2. Let me clean this up a little bit here, just so we can compare the two. And ball number 2, I'll make it in green, right? It goes like this at 25 meters per second, right? This one was going up at 25 meters per second. Okay, so they want to compare the two balls. Which ball hits the ground first? Well, it's clearly going to be, which one? The ball that's thrown downward, right? Because it's only going to do this. The other one goes up to a maximum height, turns around, speeds up. So it has to be the one thrown downward. Which ball hits the ground with the greater speed? So this one here is a little bit tricky, right? Let me go ahead and kind of give myself a little bit more space to try to explain this one. Let's think about the first ball that I throw, the one that's thrown or that's illustrated in the black. We know that it kind of goes up, it goes to 0, then what happens? Then it turns around and it comes back down. Okay, but once it gets back to the launch point, ask yourself, what is the speed of that ball? Actually, the speed of that ball is actually 25 meters per second, but it's going down once it reaches that. So it becomes kind of the exact same situation as just throwing it down. From this point on, it's exactly the same. Okay, so it has to be the same. Which ball will have a greater acceleration while in flight? They're both going to have, this is a trick question, the acceleration is minus little g or minus 9.8 meters per second squared. That's the acceleration throughout the entire trip. All right, kind of a good problem to get started. All right, problem 2. A rocket car accelerates uniformly from rest and reaches a maximum velocity of 150 meters per second through a distance of 510 meters. The boosters are then turned off and the car coasts to a stop in 22 seconds. All right, quite a lot of information here. This time is from the moment the boosters are turned off. All right, so we got to kind of put everything together. Let's look at the first problem. It says, what is the acceleration of the car when the boosters are on? All right, so you go from rest, that's the initial velocity is 0. Our final velocity is 150. And the distance, delta x, is going to be 510 meters. All right, so the question is, what is the acceleration? So for this one, I would use one of my kinematic equations, right? Plus 2 times the acceleration multiplied by delta x, because they don't really mention time here in the first part, so let's just go ahead and do this. Rearranging here, I want to solve for a, so if I just do the math, it's v final squared minus v initial squared over 2 times that distance. Now I'll substitute our numbers. We get 150 squared over 2 times 510. And if I do the algebra correctly and do the math in the calculator, I should get 22.06 meters per second squared as my first answer. Okay. Don't forget the units when you put in the box. Okay, how far does the booster coast at the moment the boosters are turned off? All right, so you're going pretty fast, right? You're going pretty fast when the boosters are on. Oops. Let's go ahead and describe this here. When it's on, right, you've kind of made it all the way to this point. All right, you've made it a distance here of, let's just sketch what's going on here, 510 meters. And my final velocity here was 150 meters per second, right? Then you turn it off. And what happens? In the next little bit, right, in this section over here, I'm going to travel a certain distance, but I do know the time for this, 22 seconds. And I know that the final velocity here at the end, v final, has to be equal to 0. Okay, so we know initial, we know the time. I guess we have to know, how do you calculate this? How far you want to know is the distance, delta x. So let's think about another kinematic equation we can use. Okay, there's another one that we can use. One of my favorites here, 1/2 v initial plus v final multiplied by time. This is kind of an easy way to calculate the displacement. Again, there's always multiple ways of solving these problems. I'm just trying to use the most direct method. Okay, so my initial velocity at the beginning of this section is actually the final velocity at the end of the first section when the boosters are on. So you should get 150 here. Plus 0 is my final, and the time is 22 seconds. Put everything in there. I think I get like 1650 meters. Let's go ahead and put that one in the box, 1650. All right, put the units in there as well. Next question says, what is the average velocity of the car for the whole trip? All right, so for this, we need to know the definition of average velocity. Now, be a little bit careful, right? It's the total displacement, okay, of the trip divided by the total time, all right? That's our definition. So the displacement we know because we went 510 in the first part, and we went 1650 in the second part when the boosters were off, okay? So that one's pretty straightforward, and we're always moving in the same direction, so you simply add those numbers to know the displacement. The question is, what is the total time? Well, we didn't know anything when the boosters were on about time. We do know it takes 22 seconds when the boosters are off, but we really need to calculate the time here for this first section when the boosters are on. We do know a lot, though, about this first section, so for this one, we know the initial velocity, the final velocity. We also know the acceleration. I think one of the kinematic equations will get us there in no time. All right, the initial velocity is 0. Let's just rearrange this. Our time then is v final divided by a. Go ahead and do that math. It's 150 divided by 22.06. So we should get, I think, approximately 6.8 seconds. All right, so let's go ahead and substitute everything in here. So we get 6.8 for this one plus 22 seconds for that last one. So the average velocity, I think once you put everything in, I think I got 75 meters per second. Okay, let's go ahead and put that. Meters per second. All right, and the last bit, they go sketch. All right, sketch the shape of the rocket motion. So what does it look like for the position, velocity, and acceleration? All right, so what I'm going to do is I will kind of break it down into what happens when the boosters are on versus off, and that'll be kind of my midpoint. All right, and this time I know, I just calculated. This was a time of 6.8 seconds. And what about the final time of the graph? The final time of the graph is when I add both of these together, right? So that should be 28.8, right, if I add those. This is the total time, 28.8. All right, so what does this one look like? Well, I do know that if I'm speeding up, right, if I'm speeding up, the sketch should look like a parabola over here when I'm speeding up, okay? What happens after that when the boosters are off? I'm still kind of moving, right, but I'm going to be slowing down, right? And when I slow down, the slope has to get smaller. Remember, the slope of this graph is the velocity. So I'm speeding up in the first section, the slope is getting steeper. This is when the slope should be 150. And then I'm slowing down, so it should be like this. I'm still moving forward, though. And this, what else can we write? We can write kind of positions over here. This here should be my 510. And the last one should be, so 510 plus 1650. Okay, I think that gives me a 2160. So 2160 is all the way kind of up here at the end of the 28 seconds. For the speed, again, now I'm speeding up and I'm going up to a maximum of 150 in the first 6.8 seconds, so it should look like that. And then what happens in the next 22 seconds, right? 22 seconds is when the burners are turned off. Again, it slows down, right? At the end, I have to be at 0 if I go to a complete stop. Again, this is not kind of the right scale, but it's just a quick sketch. How about the acceleration? The acceleration I calculated over here was 22.06 for that first part. So let me go ahead and just draw a straight line. The acceleration is uniform. Let's write the value here, okay? And then what happens over here from the next 22 seconds? The next 22 seconds, it slows down. So how can I calculate the acceleration or the deceleration in this next part? Again, you know this, you know the time. Let's go ahead and calculate the acceleration for this last section, which I haven't done yet. It's just the change of velocity over the change in time. This is a final minus an initial over that change in time. The final is 0 in this case. The initial was 150, and the total time for this whole deceleration was 22 seconds. I think I get minus 6.82 meters per second squared. So if I go ahead and add that to the graph, it should be negative down here for these 22 seconds. Let's just write the value here. All right, so I think these are what my sketches would look like. Anyway, hopefully you like this exam. I think it was kind of a fair exam for a good AP Physics test on kinematics. All right, good luck, folks. Thanks for watching.